Hello and welcome to this video where we're going to review an audio amplifier evaluation board which supports both Class AB and Class D audio amplifiers. Here we're looking at the setup. You can see the dummy load and the input signal. You see the Arduino, some signal conditioning circuitry, and the evaluation board itself. The goal is to create a user interface here based in Python to select the amplifier class. Here I'm going to select Class AB. A Class AB audio amplifier's output is a scaled up version of its input. It's a linear amplifier. I'll select Class D. A Class D audio amplifier uses a representation of its input for its output, and the way we do that is through pulse width modulation. In this video we'll review the evaluation board, the chip, and see some practical issues that I needed to overcome. I have no affiliation with the product, but I think it serves as a good example of challenges you might come across in this interesting case study in these two amplifier topologies. Let's go ahead and take a look at the systems level diagram used in this circuit in the evaluation. We first have a Python GUI. This Python GUI is responsible to send the signals to the Arduino to select the mode. We then need to condition that mode logic because the chip is expecting less voltage than the Arduino is providing. The Arduino provides a 5 volt or a 0 volt signal, and we need to scale that down to not overload the chip. That's what this mode signal conditioning block represents, which is the circuitry on the board we saw previously. In addition to the mode signal, we have an audio input signal, which in my case is either from my cell phone or from my laptop. My inspiration in getting this chip was to have a convenient way to assess the Class AB and Class D audio amplifiers. Remember that the Class AB output is just a scaled version of its input, and the Class D is a pulse width modulation output which recreates its input. When I first got this board, I was a bit disappointed because the mode was not actually working. Upon further investigation, I realized that the mode was selected by the factory because it had a 0 ohm populated resistor that tied it to a power supply. In order to figure this out, I first had to populate wires so then I can interface with the board. The chip has a few inputs. It has a shutdown, mute, and mode option. This video will just cover the mode option. After soldering the input wires, I noticed here this 0 ohm resistor after investigating the board. The 0 ohm resistor acts as a jumper connecting two pads together. So it's like a jump wire that creates a short. If you remove the 0 ohm resistor, then those two connections will be open. I'm an amateur when it comes to board work, but I was able to remove the 0 ohm resistor here. It's a very small component, and you can see the damage left at the wires here. Despite this workmanship, the board works and the pads are now exposed. I'll go ahead and add in the 0 resistor here for demonstration purposes. When the resistor is populated, then these two pins are connected. From the datasheet, that's pin 13 and pin 9. Pin 9 is the mode, and pin 13 is PVDDR, which is the supply rail. Once the resistor is removed, as you see here, the pins are now not connected. When the pins were connected, the amplifier was always selected as Class D, which defeated the whole purpose of why I wanted to get it. So after removing it, the pins are now separated and I can control them independently. I didn't modify the power supply pin, but now I have access to the mode pin. To determine the appropriate electrical interface, we'll go to the datasheet of the component. The datasheet tells us when the mode is interpreted as high and low. To be considered a high value, the voltage must exceed 1.4 volts. To be low, it must be less than 0.4 volts. So the point of the Arduino is to provide that digital signal that's input from the user. Then we go into a resistor divider that scales down the 5 volts to 2.5 volts, and the op amp also buffers that. It's a buffer because we're using the resistive divider going into the non-inverting terminal. The non-inverting terminal is very high impedance, so essentially the voltage at the divider is the voltage across the non-inverting terminal. And because we have no components on the inverting terminal and the input is connected to the output, it creates a buffer where the voltage at the non-inverting terminal is going to equal the voltage of the output. So in the context of the Arduino to the evaluation board, we wait for a user input on the Arduino side. We use the digital write function of the Arduino, which either asserts a high or a low value. We go into the op-amp voltage divider and buffer, which then provides the output to the chip's input as far as the mode goes. So that's how we select the proper mode for our audio chip. Let's now look at a couple key features to the user interface between the Python and the Arduino. On the Python GUI side, I'm using the PySide6 module. That's where the radio buttons are populated within a user window. The interface displays the text of the radio button selected, and then upon clicking the value, does the serial writes. The serial writes are one character letter that represents the user's selection. The Arduino code waits and monitors for that character, and depending on which character was transmitted, selects the proper value. Once that value is determined, the digital pin is either written high or low. Now that we understand the input stage of this evaluation board and how we're interfacing with it, let's go ahead and take a look at the component itself. The evaluation board simply allows us to conveniently interface with the PMA8406 chip. The chip itself has a functional block diagram and its datasheet to help us understand its functions. Going from left to right, we have the chip's input stages. There's an input right and an input left. We're going to use the input left for this video, only one side. Then we also have the interface control diagram, which has mute, mode, and shutdown. We're only looking at mode in this video. Next, we have some signal conditioning, the modulation stage, and then the driver stage. And there's also a couple other features with thermal protection and bias and references. Ultimately, we have the output stage, which again, we're just using the left side. Now that we've reviewed all of its sub-functions, let's go ahead and look at the system in action. We have here the breadboard with the supporting systems, the oscilloscope, the power supply, and then the 4 ohm speaker, which I have a mic hookup to so we can evaluate it. The GUI, and I'll go ahead and use my laptop and music courtesy of YouTube Studio. Take note of the current draw from the power supply for each amplifier selection. One distinct advantage of the Class D audio amplifier is that it draws less current because it's used of pulse width modulation. Thank you for watching this video, and I hope you learned something from it. Stay tuned for more content.